Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver, and today we're going to be talking about how to use those wave equations, right? So how to solve different problems using that information, because we gave you a lot, right? We said, hey, this is how you solve for acceleration max using, oscillation, right? We got equations for max acceleration for, an oscillating object, max velocity for an oscillating object, right? Where max acceleration happens where max force happens, which is the furthest displacement from equilibrium, and where max velocity occurs right at equilibrium for anything oscillating, right? We use that idea, and we got some equations, right, that told us a few things about those. So we want to know how to use those. What was the point of that, right? And then we want to know, if we are able to have a moving wave, right, equation, be able to look at that moving wave equation and be able to just pull some information out of it and see what it's telling us, okay? So let's start here with this question about a speaker. And again, if any of this isn't making sense, go watch the concept video for oscillations, because it's going to give you all the concepts for these. Like, we're walking in with certain ideas already, all right? Okay, so what we want to do is we want to go ahead and we want to read the question, right? Sorry, my brain shut off for a second. Okay, so the diaphragm of a speaker has a mass of 50 grams and responds to a signal frequency at 2.0 kilohertz by moving back and forth with an amplitude of 1.8 times 10 to the -4 meters at the given frequency, right? What is the maximum force? What is the mechanical energy of the diaphragm? Well, believe it or not, that max acceleration, right, and that max velocity gets us those answers, all right, if we know how to apply it. So, what is the maximum force? Well, like we said, max acceleration, right? We know acceleration and force are proportional, right, from Newton's law, right? So wherever force is max, acceleration is going to be max, right? We know this, and we know that acceleration's max furthest from displacement, right? There's the largest pullback towards equilibrium. That restoring force is the largest at max amplitude, right, or max displacement from equilibrium, right? So we can say, hey, if that's max, if we know that that's max force, we know max acceleration also occurs at that point. And we can use the equation that we know based off what we were given. We can use the equation for max acceleration to help us find that max force. It's that simple, right? So we know from oscillation, again, go watch the concept videos if you don't know where this is coming from, right? We know that the max acceleration for an oscillating object is omega squared times the amplitude, right? So we can use that where we know that for an oscillating object, Newton's law always applies, right? So we can say, we know the mass, right? We were given the mass, right? So we can look at this equation and say, well, do I have omega? Yeah, I do, right? I have the frequency, and omega is just 2 pi the frequency, and we were directly given the amplitude. So we'll just plug and chug from this point, right? Again, if you know the concepts. If you don't know the concepts, then this doesn't make any sense. So you got to see how the concepts fit in here, right? So we know that max force, right, is going to be equal to the mass times, and I'm just spreading this equation out, right? 2 squared, right, because omega is squared here. 2 squared is 4, right? And then the pi becomes squared. Frequency becomes squared, right? So that's omega right here, right? This is just omega, right? And then the amplitude, right? It's in the equation, which is given, right? So you just plug those numbers in, you got the max force. It's that easy, okay? That's what you want to think about when you're actually using these equations in a physical way. Like, how do I physically function with this? Okay, so the next question is asking us, what is the mechanical energy of the diaphragm? Again, well, that's great, right? We know that energy can be equal to the max potential energy, or the change in potential energy, or the max energy can be equal to the change in kinetic energy, right? Where we know potential energy is equal to 1/2 kx squared, right? Well, we don't know k. We weren't given that. We might be able to solve for that one, right? But we don't know displacement. So this doesn't help us at all. If we knew it, we could use it, right? But we also know that E is equal to the change in K, right? Where we know kinetic energy is equal to 1/2 mv squared, right? Where the max energy and I should have written it there, I wrote it down here, the max energy will occur when the velocity is max, right? And we know that occurs right at equilibrium for an oscillating object, right? So we say, hey, well, do I have mass? I do. Do I have velocity? I do. How do I know I have velocity? Because in our oscillating, when we modeled oscillation and we looked at our graph, right, we were able to make this equation, right? This equation became our velocity max. Again, go watch the concept videos if you don't know where that's coming from. So if we know velocity max, we can use this idea and get the max total energy, right? So we can start, because we said it's the change in K, right? So E max is equal to 1/2 mv squared max. That would be the final, right? After it's at max amplitude, where it's going to have 0 velocity, it's going to come back to, max amplitude or furthest away from the equilibrium. It's going to come back to equilibrium where it's going to have the max velocity, right? So we're saying that that's the final, essentially, when it comes back, right, from the max displacement point. Oops, sorry, pointing at the wrong thing. Minus, this is at max displacement point. We know at max displacement from equilibrium or velocity 0. We know this, and that's what this is trying to say in a weird way. We know that this velocity is 0 at max displacement, and that's our initial starting point. So that's going to be 0. V0, this multiplied by 0 is 0. So we end up with just this equation, 1/2 mv squared max, where V max is equal to omega A, again, that velocity that we got from an oscillating object. So again, just as we did up here, once you understand that in the concept, it is just as easy as popping V max in there. Now again, we don't directly have omega, we have this, so I did that again, right? But here velocity squared, so that means that this whole thing is going to be squared, right? It's really, that's our equation for velocity, but since velocity is squared in the E max, right, if velocity is squared, that means omega squared and the amplitude squared, right? So that's what we did here, right? Where the 2 is squared, pi is squared, frequency is squared, and the amplitude is squared, right? Because we know omega is 2 pi, all right? And then 1/2 m, we know m and we know 1/2, right? So that's the total mechanical energy, all right? It's that easy. That's how you use, maybe I should have done that in red because I did it up there because they are important. Those equations we gave you, okay? They weren't just randomly given to you, like, what the heck do I do with these things? You can use them with the stuff we've been talking about in class the whole time, right? If it's an oscillating object, right? So that's the idea. Okay, so for this next one, write equation for sine wave with amplitude 0.120 meters, wavelength is equal to 0.30 meters, and wave speed is 6.40 meters per second traveling in the positive x direction, right? So that's the idea here, right? So we go ahead and we write down what we were given because we're trying to write an equation, right? It tells us to write an equation, but I didn't start it with that. Sorry, again. My mind got distracted a second. Someone came to the door where I'm making these videos and they kind of took me, but I don't want to restart. So again, the question that we're trying to answer here is to write an equation for a sine wave with an amplitude of 0.20 meters, a wavelength of 0.30 meters, and a wave speed of 6.40 meters per second traveling in the positive x direction. That's what we're asked to do, right? So we were given a few things, right? I didn't write those down, but we know amplitude, we were given that, 0.120 meters. We were given wavelength, which is 0.30 meters, right? It tells us, right? And we're given wave speed, which is v, velocity, right? Which is 6.40 meters per second. Again, if you don't know, look at the units. The units tell you what the things are, okay? So, based off of this, right, we can write an equation where we know our general equation, I probably should have written that, right, is, if they're asking us to write it, they told us sine wave, right, is going to be, right, omega t plus or minus based off the direction it's going, right? In this case, we know it's going to be minus because we know x is going to be opposite of the direction we're traveling. So if we're positive x, then this x needs to be negative, right? Times kx. That little k and x. Okay? Sound good? So this is the general equation. We got to build this, right? And we look at our givens and we say, well, I wasn't given these directly, right? But we know them, right? So there's this little chart that I'm giving you that comes from your book, comes from a lot of books, but it helps you use it for these types of situations, okay? So this gives you the combination of what you need, okay? It's the combinations to get the values that you need in these equations, I guess I should say that better, right? So we can see that I'm kind of relating things, right? I'm trying to say that these two variables, right? Try that better. These two variables are giving us this equation, right? These two variables are giving this relation, I shouldn't say equation, this relationship, right? Sorry. These two variables are given, right, us this relationship, and these two variables give us this relationship. And you can kind of go back and forth. Like, let's say you're given lambda, right, and velocity, and you need to get here. You can go this way through the chart to get to this value if you need k, all right? Or if you're given these values and you need to get up to here, you can follow it, step 1, step 2, step 3. Or if you just need to get from here to here, you can do that. Or you can just directly just use, right, the relationship that's given, right? So these relationships can go into each other, right, and different things like this. That's important to know and see. Okay, all right. So coming over here, right, we can see that omega, right, and you'll definitely have to play with things, but if omega comes over, t goes down, period comes down. So omega is equal to 2 over period, where period, right, is going to be equal to, if we bring velocity over to this side underneath lambda, period is going to be equal to lambda over v. So we can rewrite omega, right, with period rewritten like this, where it's 2 pi v, the velocity, over lambda, the things we have, right? So cool, we have omega, right? We did that. The next thing we do is we need to solve for k, right? Well, that one's pretty easy, right? We can look over at this chart and say, hey, I have lambda, 2 pi is a given, I can just swap k and lambda, right? When I do that, I'll have k and I'll have the values for my equation, right? Because all we're looking for is this. We were given amplitude, right? So we have this, and so we're good, and that's what happens here, right? So we can see that when we look at this equation, right, we said omega is 2 pi v over lambda. This is omega right here, right? We see that k is 2 pi over lambda, right? And that's going to be that value right there, right? So we know, so that's how you use it, right? We might ask you to write the equation. That's how you write the equation, okay? Using the variables in there, right? So you want to kind of blindly write the equation, see what you need, and then solve for what you need, all right? This next one is saying the equation for a transverse wave, which is a wave moving like this, a moving wave, right, is this. We're given this equation, right? And they want to know what the amplitude and what the wavelength is, right? Or lambda, wavelength's lambda, amplitude's a. So the first thing you want to do with this equation is you need to solve it, because that looks weird, right? Can we see, right? We need to, again, turn it into this form, right? No matter what's going on. This question up here, or this question down here, we gotta keep this idea in mind. This is what we're trying to get to, right? This looks weird, right? Sine, radians, what's going on here? Right, but we know that this is just telling us that it needs to be multiplied in, right? So do that. That's all we're asking you to do. Don't freak out when you see something weird like that. I can see you didn't close the parentheses off on this end. But don't freak out when you see something weird like that. Okay, just do what you know to do with math. This is telling you to multiply it in, so multiply it in. And when we multiply it in, we can write this equation out nice, right? We can say, okay, y x t, right? Function y is a function of x and t is equal to the amplitude, which we know, right? Sine. And then, right, this pi radians over 3 times x is just that, right? So we write that, and that's our k, right? And we know that's our k because k always goes with x, right? And then we know omega always goes with t, right? So, again, we just bring this value in, so it's 66, the pi is coming from here, 66 pi rad, right? You can see this value is just right here, right? Pi rad over 3. So 66 pi rad over 3, so again, multiplying that times 66 gives us our omega, and then that t, right? X and t don't get values in this equation, so they always stay blank, right? It's a function of those. we should be given those, we can see things with them, right? So there we go, and you want to label it up. Okay, now I know my K. Now I know my omega. There's amplitude, very straightforward, right? So what is amplitude? Well, that's easy. We can see it. It's right there. Bam, done. What is wavelength? Well, we know wavelength, right, is 2 pi over K. So it's just as easy as finding K in this equation, right? K's right there, right? Not that, don't worry about the X. K is just pi rad over 3. So that is going to come into this equation, right? K is going to be substituted with that, which is what I did here, right? Where pi rad will be on the bottom, and since this is a fraction, right, that 3 is going to come up, right? So again, our final equation for lambda is going to be 2 pi times 3 over pi radians, okay? So that's, again, what you should take away from here is how to use these equations, how to use these values, okay? Because it can seem very abstract. Here it's using a moving wave equation. Right here we're building a moving wave equation. We wrote one, right? This is the equation that we wrote. This is our brand new equation that we wrote for this problem, right? This is the answer right here. We wrote an equation based off the information we were given, right, for a moving wave. Here we were given an equation for a moving wave, right? And we're able to abstract information and get the things that they wanted, right? And over here, right, we use that A max and V max, right? Those abstract things that we were given, how do we use those physically? That's what we did there. So here's 3 good examples. Hope that was helpful. Don't forget about this nice little thing, because if you're not given an equation sheet, this is a nice thing to remember to get back and forth between things, all right? Super proud of you. Keep up the good work. You're at the end of the semester, so all the hard work that you've put in up to now is going to pay off. I am extremely proud of you. I hope you reward yourself just for making it to this point in the semester. It's not easy. I know you may feel like you don't need a reward, but you should, because it's a big deal you made it till now, and I'm proud of you. Your professor's proud of you, I promise you. So keep working hard, keep up the good work. You're going to rock the end of this class, and I'll see you in physics too.